Hi, in this video, we want to take a look at point estimation in statistics. All right, the big idea here is that there is some value that I can't actually observe, but I can use data and mathematics to estimate what that value is. All right, so for example, let's say I want to estimate the average height in the United States of males, the average male height in the United States. Now, I'll never truly know what is the true average height of American males, but if I go out and I collect data, I can get a pretty good idea of what it is. I can estimate the value. The individual point, it can be estimated. This is point estimation. All right, so there's a bunch of different ways that we can go about this. The two major ones are method of moments and maximum likelihood estimation. Then after that is Bayesian techniques. After that will be least squares, and then some specialized ones that we'll talk about later in the video. Now, in statistics, point estimation is a method used to estimate an unknown parameter of a population based on observed data. There are several techniques commonly used for point estimation. Here are some of the major ones. First one, this is method of moments. All right, so I'm going to contrast method of moments and maximum likelihood first with math. Think of method of moments as solving a system of equations in college algebra. Think of maximum likelihood as maximizing in a calculus problem. So method of moments is like a system of equations, and maximum likelihood is like a calculus problem. All right, so if you're solid on your math, either one works for you, they're great. What's even better, honestly, R will do all of it for you most of the time. So even if you're not comfortable with systems of equations, even if you've never done calculus in your life, you can still use these techniques. So the big idea here for method of moments is that I can take my sample average, I can take my sample standard deviation. Now, there's going to be parameters for the probability distribution that I'm interested in. So let's say maybe like gamma, for example. Well, there's a relationship between the parameters of the gamma distribution and the mean, and there's a relationship between the parameters and the variance. And so what I can do is I take my sample average and I treat that as if it's the population average, and that gives me an equation with the relationship of those parameters. Then I take the variance and I say, hey, my sample variance, I go ahead and plug that in for the position of variance in the relationship, mathematical relationship, and then I've got two equations to work out. All right, and so depending on the distribution, this might be enough. Maybe we need to go to measure like skewness or kurtosis, third and fourth moments respectively. Then we keep on getting more higher and higher moments until we have what we need to get our estimates. All right, so method of moments involves equating the population moments such as mean, variance, skewness, and kurtosis with the corresponding sample moments. So we say the population moments match up with the sample moments in an equation, and then the unknown parameters are estimated by solving the equations. This technique is often used when you have a set of population moments, mean, variance, skewness, kurtosis, that can be equated to their corresponding sample moments. If you have sufficient information about the moments of the population distribution and want a straightforward estimation method, the method of moments can be a good choice. I like this a lot. Honestly, professional statisticians don't like this as much, but honestly, when I'm doing my pencil and paper work, trying to figure out the model that I want to work with, I find that this is a pretty easy one to do by hand. The calculus for maximum likelihood can sometimes get kind of crazy. So I like method of moments a little bit more because I tend to actually do pencil and paper math for my data analysis. Now, sample mean is going to correspond to the first moment, and we're going to say that mu hat It's our estimate of the population mean mu. Add up all of our observations, divide by the number of observations. Our sample variance is this is going to take the position of, we're going to take this value and plug it in for the population variance in those equations. So my sample variance is equal to the square deviation between observation and sample mean squared. Add up the square differences and divide by n. All right, so there's advantages and disadvantages with every way that we can estimate point values. So method of moments, the advantages are, honestly, they're relatively easy to understand and apply. They provide consistent estimators when we have large samples, and they require minimal assumptions about the underlying probability distribution. Disadvantages, the disadvantages are why statisticians generally shy away from method of moments and prefer maximum likelihood. Some disadvantages: may not yield efficient estimators compared to other methods, can be sensitive to the choice of moments used. Usually this isn't a big deal if we stick with first moment, second moment, like the lowest number of moments possible. May not work well if higher moments are not well defined or difficult to estimate accurately. Another disadvantage that I was wondering how to word it in the notes is that it's possible in some weird cases that we could actually get a value that doesn't even make sense. So if you take my statistics class on time series, one of my time series videos, I go over where you get an imaginary number for an estimate that doesn't make sense using method of moments. You can get negative values when you're supposed to have positive values. These usually don't happen in real life. If I have sufficient data, it's usually not a problem. If I have a large amount of data and a good model structure, I've never had a problem, but it could come up. All right, so let's run through an example. So here I'm using R code. Here I'm setting the seed so I can repeat what we've got. I'm generating a sample of observed data. Here I'm taking just the mean, and here I'm taking the variance and then square root to get the standard deviation. I could just have used the SD function, but because I used variance as a second moment up above, I want to emphasize variance here. And so here, this is my estimated mean, and here's my estimated standard deviation. Now, in upcoming videos, we'll talk about figuring out, do I have a good estimate or a gray area? Is it kind of good, kind of bad? We'll figure that out in future videos. Now, the next one is maximum likelihood estimation. This is the one that professional statisticians like the most. Here, we basically set up a calculus problem for maximizing a likelihood. And then when we get that maximum likelihood aspect, the corresponding value gives us our estimate. That's how we get our maximum likelihood estimator. So maximum likelihood estimation is a widely used method that aims to find the parameter values that maximize the likelihood function of the observed data. The likelihood function measures the probability of obtaining the observed data from different parameter values. Maximum likelihood estimation is a versatile technique that can be used in a variety of scenarios. It is particularly useful when we have a well-defined probability model for the data and want to find the parameter value that maximizes the likelihood of observing our data that we have in our hands. Maximum likelihood estimation tends to be efficient and asymptotically unbiased, making it a popular choice in many statistical applications. Now, here is just the math representation of what we're doing. Okay, what this is saying is I have my data that I'm observing. I have, here we're assuming we have independent, identically distributed observations. Here, this is my probability distribution function, my density from the previous video. All right, so what we're going to do is after I observe my data, that random variable is no longer a variable because I can see it. It's a constant. I have it in my hand. I'm going to plug that in. Now, to get the actual density of value from the function, I need to know what the parameter values are. And so what we're going to do here for our estimation is that if I look at this, I realize after I observe my data, the x's are constant fixed values, but the parameters are variables. And what I'm going to do is I'm going to run a little bit of calculus, and I'm going to find the maximum of that. So I'm going to find the parameter values that maximize the product of the density functions. Easy peasy, lemon squeezy. All right, so there's some big advantages with this one. This is asymptotically efficient, so it's efficient for large data sets, meaning maximum likelihood estimators attain the Cramer-Rao lower bound in large samples. That's important in a theoretical statistics class. MLE is consistent and generally, but not 100% unbiased. It's applicable in a wide range of statistical models. And so it's more useful than the method of moments for the range of values under consideration. But there are some disadvantages. One is that we need to know what probability model we need to work with. It can be computationally intense, especially for complex models, and relies on large sample sizes for the asymptotic properties to hold. So a lot of the proofs and a lot of the properties and results from maximum likelihood estimation assume that we have a pretty big data size, and that may not be the case. I may only have like 30 observations to work with. All right, so here, let's go ahead and run through a maximum likelihood estimation. And so here we have a sample data set. And all right, so my rate here is 2. This is the true correct value that I want to estimate. And we're pretending I don't know of the value 2. I just know that there is some rate for this exponential random variable. I have data. I want to estimate what is the rate of the exponential random variable. All right, well, if I go through and take mathematical statistics, theoretical statistics course, I know that the maximum likelihood estimate of the rate is 1 over the sample average. All right, so then I'll go do exactly that. I'll take 1 over the sample average, and that gives me my estimated rate. So, all right, so this is my estimation. Off of 100 observed data points, I get 1.9 as my estimate when the true value is 2. That's pretty close. That's pretty good. Now up here, I forgot to say it, but the idea here is that I want to estimate the mean and the standard deviation of the source of my data. All right, well, since this is random number generation, I know the true value. I know the true value is 3 for the mean and 2 for the standard deviation. I want to use my sample to estimate the mean and the standard deviation. So we're pretending in this example that I don't know the mean, I don't know the standard deviation of my source of data. I have some observed data, and I want to make an estimate. All right, so I know that if I take the sample average, that is the method of moment estimate of the population mean. All right, and so here the true value is 3, and we get an estimated value of 3.2. Not as close as we would like, but it's decent. And now the estimated standard deviation is 1.8 when the true value is 2. Okay, so this kind of shows that we're in the right ballpark. We're close, but not exact, because this is only an estimate, not the true value. All right, the next one I want to talk about is least squares estimation. All right, so least squares estimation is where we go and we set up so that the deviation between observed and model squared added up is as small as possible. All right, so least squares estimation. What we're going to do, we're going to take data the value that the model says it should be, subtract, square it, add them up. All right, so remember when I square it, I'm making it positive. And so what I want to do, I want to take that final sum of squared values and make that as small as possible. If that's as small as possible, then I might have a good estimate of that model. Because remember, I don't know what the true model is. I'm trying to estimate what that model is because when we're working with data, we don't know what's going on. That's why we work with statistics and data. All right, so least squares estimation. This technique is commonly used when estimating parameters in regression models. That is absolutely the #1 reason I would use least squares estimation. It involves minimizing the sum of the squared differences between the observed data and the predicted values based on the estimated parameters. So we want to minimize the sum of squared differences between observed and predicted. All right. This technique is commonly used in regression models where you want to estimate the coefficients that minimize the sum of squared differences between the observed data and the predicted values. Least squares estimation is appropriate when your model assumes that the errors are normally distributed and you want to find the best fitting line or curve to the data. And so here, I believe my assumption, my understanding of the system, maybe as like a physicist or an engineer, my understanding of what's going on is I have this equation relates X and Y, but I don't know the exact value of the intercept. I don't know the exact value of the slope. Now here, this is my random term on this. So what I'm going to do is I'm going to find the values of the intercept and slope that minimize the difference between the observed data and the predicted value squared, all added up. All right, so that means in a sense, I'm trying to minimize the difference between my observed data and my model. Now, the advantage is to this provides a unique and explicit solution in many cases, often leads to easily interpretable estimators. This is efficient under the normality assumptions, but there are disadvantages. There's sensitivity to outliers as it heavily weighs influential observations. All right, so if I have a large Y value in my data sets, what it can do, potentially, depending on what's going on with the rest of the data, if this is super, super big, imagine I've got my Y values are 1, 5, 2, 3, and 4. Let's say 1, 2, 3, 4, 5, and 10 million for my Y values. All right, so that's kind of lopsided. What's going to end up happening with my regression model is basically my regression model is going to try to minimize that 10 million and ignore the rest because proportionately the rest is so small, they're not significant. So outliers can throw this off. We have to watch out for it. So another disadvantage is that errors, it assumes that errors are normally distributed and have constant variance. And this may not be appropriate if underlying assumptions are violated. This can actually be weakened a little bit, but the constant variance, this has to be true. We make the assumption that errors have expected value of 0 and constant variance. Normally distributed is if I need that if I want to do like hypothesis testing. But we could weaken the assumptions a little bit, but not very much. Usually doesn't make a difference in real life data. All right, so now let's go ahead and run through an example. All right, so what we've got is that the true slope is 2. So here's the slope, 2 times x, slope is 2. You'll notice that there's no intercept, the true intercept is 0. And then we have that random term, that epsilon that we looked at a moment ago. Now what I'm going to fit a linear model. And now I'm going to use the coefficient function to get the coefficients. The first one is going to be the intercept. The second one is the slope. And so we get our estimated intercept and slope. So remember that my true slope was 2. All right, so we're pretty close there. We did a really good job. Now, when it comes to the intercept, the correct intercept is 0, and I get about negative 0.2. And so it didn't do as well on the intercept, but you know, it's still in the right ballpark. If I had more data, I'm sure I would have had a better estimate. Now, Bayesian information. Bayesian estimation takes advantage of expert knowledge, beforehand information. All right, so the classic way of approaching statistics is that my prior knowledge, my prior experience, my understanding from working 20 years in the field means nothing. The only thing that we care about in classic statistics is what the data says. This is called the frequentist approach. And honestly, it does a pretty good job. But there's times and situations where we want to pull in information from experts who work in the field constantly. We can actually get better results for our models if we pull this in. Bayesian statistics is the #1 way of pulling in expert knowledge about what's going on. So Bayesian estimation incorporates prior information. So prior information, the word prior is going to come up again, or beliefs about the parameter into the estimation process. It uses Bayes' theorem to update the prior belief with the observed data and obtains the posterior distribution. All right, so the idea here is before anything happens, before I collect data, I have prior understanding of what I'm working with. I've been working in the field for 15 years. I have insight, I have knowledge. I know what's going on. I've got a pretty good idea of what's happening with it, but I don't have like data to back that up. All right, so I take my previous established understanding of what's going on, I take my data, I put them together, and I get a posterior distribution. And from the posterior distribution, we make our point estimate. I personally like Bayesian estimation in the situation where I need a more complete representation of what's going on, or I'm in a small data situation and want to fill in the blanks with the prior. A lot of times, a lot of biological and medical researchers like Bayesian statistics over the frequentist point of view. Right. Bayesian estimation is useful when we have prior knowledge or beliefs about the parameter that we want to estimate. By incorporating prior information and updating it with the observed data using Bayes' theorem, we can obtain a posterior distribution from which point estimates can be derived. Bayesian estimation is valuable when you want to quantify uncertainty and make probabilistic statements about the parameter of interest. All right, so the posterior distribution is my prior distribution times what I get from my observed data. So I take my observed data, I take my prior, put them together, and that gives me my posterior. And so then I can use this posterior distribution to get the estimated value. Now here, I'm showing it as an expected value, but it could have also been a median or a mode. All three are reasonable. Now, some advantages of Bayesian estimation. All right, so this is the only one that really allows us to incorporate prior knowledge about what we're working with. This provides a posterior distribution, enabling uncertainty quantification. So there's some more tools that we have to work with when we do Bayesian estimation. This handles small sample sizes very well and can yield stable estimates. Disadvantages. All right, so this requires the specification of the prior distribution, which can really be a subjective or challenging thing to get at. All right, so it can be subjective in that two different subject matter experts would say two different distributions. Another thing is that if I'm working, for me as a statistician, this is an issue I've had professionally, is that my subject matter expert knows what they're talking about. They're experts in what they do, but they don't know how to use words to describe the math that they intuitively understand because they don't have that math knowledge to bridge the gap. And so as I'm talking to them, I'm trying to pull the information out, but it doesn't always work out. I'm in that situation right now, in fact. Bayesian statistics can be computationally demanding, and this is not a joke. The Monte Carlo Markov chain can take a long time, and this is especially true for complex models. I have ran things overnight. I have ran things and gone to lunch. I have ran things at the beginning of the day and had them in the end of the day. So this can take a while. Also, Bayesian estimation can be sensitive to the choice of the prior distribution and its impact on the posterior estimates. All right, so it's possible that if I choose a prior that puts a lot of weight towards one particular value, a very narrow range on that probability distribution, it can work out that my data basically doesn't get to influence what's happening. And so, practically speaking, at least. And so that can be a disadvantage. This is why you'll hear people talk about uninformative priors. All right, let's go ahead and run through an example. And here we're going to use RJAGS. I've used RJAGS professionally, by the way. It's been a few years. Here I'm setting seed so I can repeat this. And what we've got going on is that we've got a coin that isn't a fair coin. It has a probability of 0.3. 30% chance of heads. We're flipping it one time each, and we're going to flip it 100 times. Now, what we're going to do, we're going to do the classic introductory Bayesian estimation problem of using the beta distribution. Here, this is going to be uniform beta as our prior. So this is the uniform distribution. What we're doing, we're saying I have no prior knowledge of where the probability of heads or tails would be. And now I'm going to go through and do my Bayesian modeling here. And so now I'm just setting up my data, putting things into the right format to work with. And then I put it into my JAGS model. And this can get a little bit complicated. DataCamp used to have a really good RJAGS course. It's where I learned. After I took that course, I started using it at work. All right, so now, after I get this all done, my estimated probability is 0.29. Now, where this can be advantageous is, let's say I only had, let's say I had 5 data points, not very many, but I had subject matter experts that was able to tell me, I think the probability is around 0.35. Let's say 0.35, something like that. The person who I'm talking to, they have subject matter knowledge. They say maybe a third. It's a little bit high. They say, you know what, Smitty, I think that coin, I've been playing with it. I think it's going to come up, as a probability of heads at 1/3. I can adjust these parameters to get 1/3 to be the central tendency. Then when I drop it, even if I have small data, I'll end up getting a pretty good estimate, which I think is really, really cool. All right, the next thing I want to talk about is percentile estimation. All right, we use this when we compute medians, also when we compute box plots and interquartile ranges. All right, so percentile estimation involves estimating a specific percentile of the probability distribution based on the corresponding percentile of the sample data. So here I'm interested in, I want to estimate, where is the 50% mark, the halfway mark on the distribution? Well, that's the median, right? The median of the population, which I'll estimate with the sample median. I'll take the Q1 to get the point where 25% of the data is less than or equal to that value. And that's going to be my estimate of the population's first quartile cutoff. Do the same thing for the third quartile cutoff. I take the value where 75% of my data is less than or equal to that value. And that's going to be my estimation of the population third quartile. When you are interested in estimating specific percentiles or quantiles of a population distribution, percentile estimation is appropriate. This technique is often used when you want to estimate values such as the median or specific percentiles of interest. It can be useful when you are primarily concerned with a particular portion of the distribution rather than estimating the entire parameter. I'm actually, this past week, I used this with Vingantiles. So the percentiles were corresponded to 0, 5%, 10%, 15%, all the way up to 100%. Now, advantage of this, percentile estimation directly estimates the specific percentile of interest. It's robust to outliers and does not assume any specific distribution. That's really, really nice. Relatively simple to compute and interpret. I mean, I can do this by hand as long as I can write my data in an ordered format. Some disadvantages. Provides limited information about the parameter beyond the estimated percentile. So it's harder to tell, do I have a good estimate or a bad estimate? May require a larger sample size to obtain accurate estimates, particularly for the extreme percentile. So if I want to figure out what is the 99th percentile, that is 99% of the population is less than or equal to a particular value, it can be hard to do that because it's such an extreme value. And this does not account for the entire distribution or shape of the population. All right, so to do this, I'm going to generate some random normal data. The true median is 0. So I want to get a value close to there. The value I want to estimate with my sample is 0. Now we're pretending that I'm collecting data and I don't know the actual value is 0. I want to estimate it. And so if I run median, we can see that I get 0.06. Pretty close. Now, the next one I want to talk about is specifically used in survival analysis. So survival analysis is frequently when we're interested in, people dying from diseases. And we start, studying people, we look at people, but unfortunately, or fortunately, depending how you look at it, the subjects live longer than the study. So I can't use their death as a complete piece of information because I just know it's in the future. And so what we're saying is we have censored data. We know that they live to the end of the study. We don't know like when they actually die. So when I have it like, I know it's greater than or equal to a value or less than or equal to a known value, that is censored data. So we have lower or upper limits on the measurements. Methods like maximum likelihood estimation or survival analysis techniques can be used to estimate the parameters. So if my data contains censoring, meaning some observations are partially known or subject to limits, techniques such as maximum likelihood estimation or survival analysis methods are suitable. These methods are designed to handle censored data by accounting for the information available and estimating the parameters accordingly. And so here is a censored data model. And here is the actual estimated value. So what we observe is the minimum of these two values. And we want to estimate the theta value. All right, so advantages. So method of censored data handles data with censoring when some observations are not fully observed. We know that they're greater than or less than a known value. This allows for estimation of parameters in the presence of truncation or censoring, provides consistent and efficient estimators under appropriate assumptions. Disadvantages. Requires assumptions about the censoring mechanism and its relationship with the underlying data. Complexity increases with the presence of multiple types of censoring. Almost always when you hear people talking about censored data, they only talk about one type. And this can be sensitive to the assumptions made about censoring, and incorrect assumptions can lead to biased estimates. All right, so let's go ahead and run through an example with R. Once again, I'm going to run through this here's my observed data, and I want to make an estimate of what's truly going on. But now, here's the kicker. If the sample value is less than 2, we're going to say It's just 2. Okay. And so now I'm going to go ahead and load the survival library. Going to run the survival function on censored samples, and we'll say that those depend on the intercept, because we don't have any other predictor variables here. Here our distribution is Gaussian, and then we run the survival regression function, and then the coefficients give us the value, and here we get our intercept of 0.34. Sorry, 3.4, which is, not too far off. It's definitely, if I had more data, probably would have given me something better. All right, so now here are some common point estimation functions in R. So one thing that you'll notice is that a particular value to be estimated may or may not have multiple techniques. And so if it has multiple techniques, you have to pick one. And you have to choose based off of your audience, your stakeholders, and what are you comfortable with. I find that frequently my students prefer method of moments just because they're more comfortable with that level of math, because it's a college algebra problem instead of requiring calculus. All right, so here the parameter I want to know is the mean. For method of moments, I'll use the mean function. Boom. Variance, method of moments techniques, is the variance function. Standard deviation, method of moments, will be the square root of the variance function, or standard deviation. Now, these are going to deal with maximum likelihood estimation. Probability of success, we can use generalized linear models for that. This is referring to logistic regression, by the way. The rate parameter that we talked about previously, maximum likelihood estimation, can be an optimization method. And probability or density parameters can be estimated using an optimization method. And so here, the optimization methods are that we're letting the computer iterate and try to figure out what's the maximum value instead of sitting down and doing calculus ourselves, pencil and paper. Now, if I want to estimate intercept, slope, or just general coefficients in regression for least squares estimation, I'm going to use the linear model function. That's shocking. Now, success probability, if I'm using Bayesian estimation, I can use RJAGs, RSTAN, or other Bayesian packages. There's a bunch of Bayesian packages. I have most experience with RJAGs and RSTAN. Now, for percentiles and quantiles, we can use percentile estimation, and we can use the quantile function to do that for us. If I'm interested in the median in particular, I could use the quantile function with 0.5, or I could use median. Either way, it will work. Median is going to be the better choice because it's specialized for the problem. And then survival or hazard parameters, I'm going to use the method of censored data, and I'm going to use the survival regression function. It's important to note that the choice of the estimation technique depends on the specific context, available data, and underlying assumptions, and the objectives of the analysis. It's often beneficial to consider characteristics of your data and the assumptions of each technique to select the most appropriate method to your particular situation. And here's some homework for you to knock out. All right, I'll leave you with this table. And that's all I got for you. Life is short. Do math.